Hello, everybody. Hi again. Good afternoon or good morning, wherever you are. My name is Gopi, and we are going to discuss a few things about. All right, so here it is. The idea here is to bring a little bit of rocket science onto your desk. My name is Gopi, and I'm a field applications engineer at Wurth Electronics for past 7 years. Agenda for the next 30 odd minute is to bring a kind of a crash course on a GNSS, know everything about the background and history. That will take us first 10 minutes for the first two items, but then we dive deeper inside looking at the modules, how you can bring that onto your electronic circuit boards, what tools available, and what sort of software and the technical supports that you can download easily to use free of charge from our online website. So without a delay, let's go. Now, how does a satellite orbits, or what if you want to launch your own satellite, what do you have to do? First of all, consider Earth gravitational field, which is 9.8 meter per second square. And if you go away from Earth, it gets lower and lower or diminished, but it never disappears. Take an example of a moon. It's still far, but it can affect us in terms of tidals and the water levels and so on. Now, moon is located at nearly 250,000 miles, but it's rotated, or it spins, or it continues to move in a space at 1 kilometer per second. Now, who decides that speed, and what happens if you increase or decrease the speed? Now, that brings us the second topic, speed and a distance. So if you bring a satellite or any moving object to an altitude high enough and a speed faster enough to counterbalance the gravitational pull, then that object remains into that orbit indefinitely. And that will require one more final piece of jigsaw, which is a friction. So about 200 kilometers after the Van Allen belt, there is not much frictions left. And what does that mean is apply the Newton's law, any of the Newton's law of motions, which is first one, for example, is actions and reactions are equal and opposite. The second one is an object remains stationary or keep moving if there is no external forces acting on it. So in a nutshell, if you go away from gravity, if you go fast enough, and if you counterbalance all the forces together, and every now and then give a little bit of throttle, that particular way you can stay in that orbit for indefinitely. And that's how almost any satellite works. Now, is there any maths or a physics behind it? So let's look at some numbers, and you don't need to remember. Nobody will pay you money for remembering that unless you are a student, but it's ideal to know exactly how the science works. So the later 15 minutes we'll talk about it will be useful to know the first 10 or 15 minutes. So G here is a gravitational constant, which is around 6.67 into 10 raised to minus 11, which is very small number, but makes a big difference. M, capital M, is a mass of Earth, nearly 6 billion trillion tons. Too big number, but so the too big and a too small number, they attract or counter-interact each other. Now, the radius of the Earth is 6,370 kilometers, but the satellite orbits at particular height, and that's where you have the next item, orbital radius, which is height above sea level plus the radius of the Earth. Then we need to bring the velocity of an object, or orbital speed, or angular speed, angular velocity, you can say. But remember, at that particular distance, really far away, there's no such thing as a really curvature. It's almost a straight line when you talk about thousands of kilometers. And then it also brings a centripetal or a centrifugal kind of an acceleration force acting onto satellites because of the gravitational pull. Now, combine all these things, and you may wonder about, can I also need to account the mass of a satellite or weight of the satellite? Ignore the spelling wrong, by the way, because it took me 10 minutes to work out this entire presentations. So mass of the satellite is really, really nothing compared to the mass of the Earth, and hence we will ignore that. Use these equations. If you want to launch your own satellite into the space, you need to travel at certain speed. Velocity is equal to square root of big gm over r, and then you need to counteract the gravitational pull by accelerating away from the Earth by using simply find the v and then square divided by r to get the speed. Here I have created a small table. So ignore all the big numbers, but yellow highlighted numbers are one for the Earth, which is 9.8 meter per second square gravitational pull for the Earth itself. And if you look at the moon, is 0.16. And that's where if you then then enter those numbers inside the formula, it will give you the speed. Perfect. That doesn't make us happy at all. But what we want to focus for the next 15-20 minutes is look at the 4 constellations that we will talk about it more often. They are GPS, GLONASS, Galileo, and BeiDou. Okay, here I have a picture taken from almost like a GPS governing body, and right in the center you have planet Earth, and then on the orbiting side you got the satellites are orbiting. Here is my version of the Earth. You can see it, and each rubber band depicts the orbital space for each individual satellite or a constellation of satellites. We will also look at that, how many sets are there per constellation. Now, I want to give you about 30-second talk onto how to read this diagram. So you've got a vertical axis on the top where you have Galileo and GPS, where you see that's the orbital period, how long it takes for a satellite to orbit the Earth. Start on the planet Earth. Of course, if we travel with Earth, so it would take 24 hours if you stay there. But if you go further away, then it gets slowed down. Any question? I see a noise in the background. Okay, maybe a question in the chat line. But that's vertical upline. Vertically downwards, you can see orbital speed, and we will also talk about what speed you have to travel, how long it will take to complete the circle to the Earth, and then what you have to do if you don't want to complete the circle to the Earth also. Then horizontally on your left-hand side is a radius or the orbit or height above sea level. And then on the right-hand side, which is where you see the Hubble, which is the height above sea level in terms of kilometers and miles at the bottom. Okay. GNSS stands for Global Network of Satellite Systems. There are 4 major constellations: GPS, GLONASS, Galileo, and BeiDou. There are 2 regional constellations, NAVIC and QZSS. So NAVIC stands for Navigation for Indian Constellation, but NAVIC also means in our culture, in Indian culture, is sailor. So a sailor in terms of a person who goes to the sea and then needs to navigate based on a certain aspect. So that's NAVIC. And Kozi Zenith satellite system, that is for the Japanese version of the regional constellation. Now, all 6 of them are talk to each other, and they all at some point merge and continue to evolve their technologies. There are more than 200 satellites orbiting at the present, and they are all working to guarantee a signal of at least 4 satellites onto every inch of this planet. They're all based on a National Maritime Electronic Association, so NMEA protocol. There are 4 different ways you can orbit over there, but all the blue part is what we want to talk about it, especially our satellite, our GPS, GLONASS, Galileo, and BeiDou operates onto MEO, which is medium Earth orbit, around 20,000 kilometers up. Orbital radius is 20 to 26,000 kilometers. Orbit time approximately 12 hours. Then there are other orbits, for example, low Earth orbit, LEO. That's where all the Hubble and Iridium kind of satellite orbits. Then you got a high Earth orbit, around 30,000 kilometers above our head. Then you got a geosynchronous. So these are the orbits that stay stationary with respect to Earth, and they take, guess how long? 24 hours to complete, but they never complete circumnavigate. They always rotate together. So if this is Earth, for example, and this is a satellite, then they all rotate together simultaneously rather than completing in 12 hours. Then There is a graveyard orbit, which is just around 300-400 kilometers above the geosynchronous orbit. And graveyard is where you park your satellite, which is out of MOT or doesn't work, or something is wrong with that. Now, what is the development over the time? So nearly 50 years ago, US launched the GPS versions, and it's on a medium Earth orbit, 20,000 kilometers above the navigation. Then immediately after 2 years, they launched ISS, which is International Space Stations, 400 kilometer. And immediately after that, you can see the USSR also launched the GLONASS version stuff. Now the question comes, why they launched the satellite at such a high altitude? It's because any military, if you have a higher location, so higher placement, then you get a little bit vantage point, and no one can counter attack, or no one can fire a missile onto you. But now that is not the case. Okay, ISS is the only occupied object outside planet Earth. It's constantly fixed with few people all the time in, and there is a shuttle going back and forward. This year alone, myself, my family, and about 20 other neighbors have watched ISS more than 4 times. If you want to watch it, there's an app you can download, or go out for an evening walk and watch a very shiny object moving in a straight line really fast. The visibility period is approximately 3 to 5 minutes, and you have to be really lucky, and I'm one of them. Okay, then nothing happened for nearly a decade, unless the Hubble came in for the optical analyzers and Iridium for communications like voice and data. But then suddenly everything picked up back in 2011, where the European launched the Galileos and Indian launched the Navik, Japanese launched the Quasi Zenith, and then Elon Musk came in 2019, where he started to launch almost like 10 satellites per day, and his thing's called Starlink. If you download an app, or if you actually go to the space, then you wander around, you are more often likely to strike with a Starlink than anything else. And then recently, Chinese launched the BeiDou, which is BDS version or a BeiDou, and there are 35 satellites in a medium or geosynchronous Earth orbit. I hope you guys are enjoying so far. And until now, probably 90% audience will not be able to make any money out of it. So now we lost nearly 10 minutes, and let's dive a little bit slowly to learn deeper insight and understand how this technology, how the rocket science can actually help you, your company, and the people around. So different GNSS signal coexist. And when I mean different GNSS signal coexist, means there are 4 constellations and 2 sub-constellations. They all bombard frequencies every now and then. So even if you don't do anything, there are at least 6 satellites on top of you. But remember, like there are more than 250 satellites orbiting, 200 active currently, right in as we are speaking. So there could be a multiple signals appearing to my satellite receiver. What main band that we are going to talk today is L1 band, which is based on a 1.5 gigahertz frequency, and that is largely applicable for civil and commercial applications. Now, there are 2 ways you can get the signals in. One is onboard active amplifier active antenna. Another one is you can use a piece of wire or ready-made antennas like this WEMCA, which is Wurth electronic multi-layer cheap antenna. You can use it for GNSS as well as 2.4 gig radio and sub-gigahertz. Then here is a really nice chart, what's evolved and what are the bands operating at various frequencies. Ideally, as I said before, that we only talk about the L1 band, because L1 bands allows like sort of a navigation for car, motorbikes, and so on. Accuracy 1.5, 2 meters. You don't need to be so precise. We look at it, by the way, what are the pros and cons for each different techniques. Now, 4 major constellations, we talked so much about it. Now let's dive a little bit deeper inside. And you remember first constellation is the oldest one, GPS. 1978, US started, and their aim was to cover the entire world for navigation signal. And remember, all these signals coming out of the satellite are one-way signals. So you can only receive them if you want, but you cannot throw the signals back to it. That's how it works. Accuracy at that point was 30 centimeter to 5 meter. So pretty good at that time, but now people want better accuracy all the time. There are total 77, only 31 in orbit at the present, which is half of them into the graveyard. Now, orbiting altitude is 20,180 kilometers. Not much, but at that time was really good, and it's still active and it still works. And remember, a lot of other people also followed, like GLONASS. They stick to the same 19,100 kilometer orbiting period, precisely 11 hours, 15 minutes, and 44 seconds. Accuracy has gone much better. Look at it now, from 30 centimeter to 3 centimeter accuracy. But that's not it. So this is Russia back in 1982. What European did is this accuracy up to 1 centimeter. Now this is precise, 1 centimeter accuracy. You can land something on your penny or a coin cell from a space. So that's really nice, super accurate there. There are total 30 satellites and all of them are present. None of them gone to graveyard yet. Eventually they will go, but keep an eye on it. Now, orbiting altitude, they went much higher than average, 20,000 kilometer. These are 23,000 kilometer. Cost is much less, $10 billion or 10 billion euro, much lower compared to the GPS at that time. Then Chinese launched that 10 centimeter to 360 centimeter or 3.6 meter accuracy. There are 35 satellites orbiting in a multiple of the altitude, so 20,000 kilometers for the medium Earth orbit, or they also go into the high HEO or geosynchronous one. All right, we are almost halfway and we have 20 odd minutes to go. So now our job is to look at what product is available or what product can you use it into your product. So sometime if I open this kind of post-it notes, I see nothing inside, but this time I see, if I open a post-it notes, I see 4 satellites mounted across this one. Well, 4 satellite receivers mounted across there. I'll bring the picture in a minute. Just wanted to show you. First is Ilara 1, has an onboard antenna, and because the name is a little bit short, Ilara 1, and it can cover GPS and GLONASS. It's a 10 by 10 millimeter and 6 mil high. When you look at the Irinome, the name is slightly longer than Ilara, and longer name means it has also got much better features. For example, Galileo's and BeiDou's. Slightly bigger, and this is the only module that can operate at 3.3 volt. The rest only operates at 1.8 volt. You have to be careful about it. This version 1 has got onboard antenna, and those who want external antenna for any reason, you go for Ilara 2. You need external antenna. You can use a active or a passive antenna, including WEMCA. It's used to be one of the world's smallest GPS or GNSS receiver. And here I put 4th one, and you can see comparisons for all 4 of them. Okay, so Ilara 1, Irinome 1, we are talking about the size wise, yeah? So Ilara 2 is the smallest one, then Irinome 2, then you have Ilara 1, and then you have Irinome 1. Then the final part I also put down is Adrestia, which is LTE module. It's a surprise, but you're going to see it in a second. And then the last red part that you can see here, that is a radio that we integrate together in order to bring signals from outside to inside. Okay, so what are the common features within this GNSS module? Hey, stop reading, guys. Please don't read this one. I get paid to read this. So I also wanted to explain and talk about it. So integrated LNA, which is low noise amplifier, integrated SAW filter, surface acoustic wave filter. You have internal TCXO, temperature control crystal oscillators, and real-time clock RTC. Now, these are the tremendous features. So you expect the price is going to be slightly higher than average. Then the sensitivity is minus 165 dBm. If you look at any ordinary 2.4 gig radio or sub-gigahertz 868 meg radio, for example, the RX sensitivity is minus 100, minus 110 dBm. This is -165. So signal to noise ratio and a SNR is much better on these devices compared to any other RF amplifier. It can do UART, I2C, and SPI, all three in one go. Almost every product has a built-in this features, that one. They currently at this point use a Qualcomm Surfstar version 5E chipset. They all follow NMEA protocol, and NMEA protocol, you probably know what does that mean, is you have to follow, send some sort of data from a module to the microcontroller. And those data, you can guess what you could expect is, for example, altitude, longitude, latitude, speed, orientation with respect to the North Pole, and timing. So these are the fundamental information you want from any GNSS receiver, and that's what the NMEA stands for. And NMEA also wants one more thing, is baud rates. Olden days, 50 years ago, 4,800 bauds was a good, so continue that way. They all, in Europe, it's certified with a CE conformity. I was told that you probably don't need a FCC or RED certificate simply because these are receiver devices only, but you play according to your company rules and regulations. Now, they all operate 1.8 volt, except the Irinome 1, 3.3 volt. Now, they all have a low power. So when they are hardly working, 80 microamp, they probably do nothing and go to sleep, or working hard and you get 55 milliamp. Well, you need to supply 55 milliamp with a pulse current considerations. Then operating frequency is 1.5 to 1.6 gigahertz band, 10 hertz update rate. What does that mean? It can talk to satellite, well, not talk to, it can listen to satellite and give you updates 10 times per second. Not that you want to travel that fast, but it gives you a signal or the update every 100 millisecond. Some people use it for the drones. It can fit really nicely. 1 PPS, which is 1 pulse per second. How does that work? I power up this receiver now, for example, and indoor, I usually get a signal if I pop it across this window. And on a good weather, I should get a clear signal. But the 1 PPS will start pulsing the LED in the middle. So you can see the 2 LEDs there, but 1 LED in the middle will start pulsing the moment it sees, or the moment it locks with more than 5 satellites, 5 or more satellites. Or indirectly people call fix, get a fix or get a 3D. Then how long it takes to power up and get the satellite sync. So if you do nothing and just power flash, it could take up to 28 seconds. And if you then go to sleep or hibernate and then wake up suddenly by a wake up pins, then it will take 1 second to get the satellite signals and then start giving you data out. They all operate on L1 band currently as we speak, and accuracy we publish on a data sheet says 1.5 meter. Apply your luck, try it, you might get it much better accuracy, you might not get it 1.5. It depends on how many satellites that you have up above. Now 2.5 meter vertical or altitude accuracy, 0.1 meter ground speed accuracy, 30 nanosecond time sync with respect to UTC, universal time constant, and they're all industrial operating temperature -40 to +85 degrees Celsius. And you can use free download WENSS, Earth Electronic Navigation Satellite System software for computers. Okay, now let's take an example. How many pins do you need to connect to your microcontroller to bring any GPS or GNSS receiver back to your circuit board? And that's what the topic is, bring rocket science to your desk. In order to do that, you just first of all supply and ground, as you can see, red and black. Then kind of an interface. In this example, it's a UART. Kickstart, your microcontroller will start seeing, because these are master devices, they continuously send data unless you hold on and off, you turn off, or you keep on resetting that one and so on. But if the power up, once it starts seeing the signals, you will see all the signals coming out of it. Now, the question is, how it does UART, SPI, and I2C just from these pins? You can read a user manual, which is around 190 pages long, or I give you a hint, which is Upon power up or before power up, you do kind of a combination on RTS and CTS pin. So request to send or clear to send, these are the two pins that if you pull up or pull down, then it will decide whether it's a UART, I2C, or SPI communication. Okay. Now, we have around 10-15 minutes to go, and I think we can cover a lot more. So these are the really information slide. Go to website called we-online.com and navigate yourself to navigation systems. I think it's a navigation system or GPS or GNSS /. Then what you can find on that is a datasheets, user manuals, CAD files, including Altiums and Eagle libraries. You get a step file for 3D modeling. You get SPICE models for simulations if you want to do that. Not all simulations available off the shelf, but please let us know. We may be able to help something. Then you have app notes, GitHubs for direct examples and downloadable SDKs, tutorial videos, there are plenty of them. You can order free samples, literally click on that and the sample baskets will appear, order samples, and you probably will get it in a couple of days' time. Technical support, you can request or you will have a pop-up and then you can ask questions there and then straight away. You may be able to download certificates such as like FCC, RED, and so on, or UL in some cases. Software download, like a GNSS. Antenna choice, it gives you matching antenna, so you don't have to do too much Google about it. And then also gives you an applications ideas. Now that takes us to one more slide called application ideas. What do you think about it? Here is a simplified version. Signal comes from a satellite one way to ILARA 1 or Irinome 1 or ILARA 2 or Irinome 2 or XYZ, or even the Adrestia 1 LTE module. Signal comes in and I could hardwire and get it to my micro, but in this example that I'm using it currently, I have a Thione 1, which is 2.4 gigahertz radio. I show you both simultaneously. So the signal comes to ILARA 1, and then it goes to this radio, Thione 1. You can use a Satebos 1 because Satebos can give you Bluetooth connectivity as well as 2.4 gigahertz proprietary or a mesh connectivity, and that is a really good advantage. But hey guys, a question or a prompt I wanted to tell you is that where does all this name come from? Irinome, ILARA, Thione, Proteus, Satebos. These are the moons of outer planets. So if you look at the Saturn, there are nearly 90 moons. Jupiter's, there are plenty moons and so on. So all the name comes from moons of outer planet. We only have one moon, so the name is a moon, but outside there are plenty names, and we started using it. Here is the signal that we talked about it. Okay, so that signal comes to ILARA 1, and instead of going to the microcontroller via one of the header jumper or via the micro USB, it goes to this radio across here. Thank you for selecting a much bigger screen there. So it goes to this radio, and you can see if I reset the radio, turn on, and reset the radio. So you can see the pulses started. I hope you can see the two pulses across this finger are happening, and that means the data started sending out from there. Thank you, really appreciate it. I wasn't expecting that. Okay, so then the data goes out, and I could receive it via another small module or use a USB stick to get it and plug it on, run the program, and you start seeing that 11.5/200 baud rates, and job done. So here is a slightly bigger picture of what we were talking about it. You need a level shifter because it's 1.8 to 3.6 volt interface or a 5 volt for the USB. Then you've got a module in the middle, multiplexers where you want to send the data to FTDI chip, which is the USB, to a radio or to your microcontroller header. And that's where the 6-channel multiplexer comes and the radio is mounted there, and inside a USB stick you also have a radio. Now connect all these things together, you get a rocket science on your desk. Okay, here is a picture of a product actually mounted outside my screen, outside my home office. I work from home, by the way, and I put all these things around, otherwise you should be able to see the bit more stuff. But this is actually dangling outside my home, powered by USB stick, and the signal comes from there to the computer. And on a good days, I can bring that in. We get the signals done. But now, today, a little bit dull. I might not get a signal, so I didn't want it to risk. And I run it, but if I run live, then you know my coordinates, longitude, latitude, and you might come here and say, hey, Gopi, now we need help. What can we do about it? So I mask my latitude, longitude. You don't see it. But the good job is you have a fix, 6 satellites there. Mind that I took the screenshot last week when I submitted that, but the same thing is happening exactly as we speak now. And I'm at 213 degree facing this way, but if I orient just a circuit diagram this way, it will give me precisely what it works. Now, what you expect from NMEA based signal that is coming in, right? You can see in the middle line, the bluely highlighted. You get longitude, latitude, altitude, polarity angle, speed, UTC time constant, number of satellites, you get it, constellations, which constellation you're currently working on. You also get signal quality or a signal strength, and you have a chance to overlap on a show on a Google map. And if you click that, it pinpoint literally right in front of your door. Then we only mentioned so many things here, but this is another screen when I go to the next level. So if you go here, is a main screen, but when you go inside a satellite, configuration, utilities, and support. So I'm now going into second tab called satellite. And on the satellite tabs, I see how many satellites I can see that, what systems they are operating, mainly GPS here, and you got a signal to noise ratios and whether I'm using it for my communications or as a fix or not. So you got yes and no. All these modules and all the GNSS receivers are simply plug and play, works with a simple USB micro cable, and default baud rate's 4800, but when you use a USB stick, make sure that you use a baud rate 115200 because this radio works incredibly fast compared to the GNSS. Okay, I think we are approaching almost to the end, and let's cover for the last couple of minutes LTE or a narrowband IoT with GNSS on board. It's one of the brand new module, and I wanted to bring a picture. Just please don't have to do it, but I will show you. Here is a LTE module, the address tier 1 LTE. Perfect. Address tier 1 LTE is the module, and I have a thank you again. Okay, so I actually powered up, guys. This is cool. Keep it. I wanted to share this information. So I have LTE module operating right in the middle, and you got FTDI chip with a multiple UART interface, and you got 2 antennas there. One for LTE band, which is the 3G or 4G, and then you got another antenna for GNSS, and they're both working pretty good. And you can insert your SIM card there, so you can connect to the LTE. And thank you. Let's go back. And so now, what are the benefit of using LTE versus just a standalone dumb GNSS? First of all, it's an integrated GPS and GLONASS built in. Not everything, by the way. You don't get all the constellations just there. Now, built-in cellular category M LTE, which is long-term evaluation, and narrowband IoT. So when you don't have enough signal strength, you fall back to NB-IoT. 3GPP, third generation partnership program built into that one. It has got an incredible feature called user system on chip microcontroller or ARM Cortex M4 processor built onto that. So you as engineer don't need to use any additional microcontroller. If program can fit within 1 MB, try. And it has also got a 256 kilobyte of RAM available there. And output power falls into class 3, which is 23 dBm, much higher power, but come on, this is a LTE design. Supports 3GPP, blah, blah, blah. it's an IoT, so it has got all the features of an IoT. Instead of going via Wi-Fi and you get your MQTT, TCP/IP, HTTP, HTTPS, DNS, MDNSS, TLS, and so on, it's all built into this one. You never have to worry about it. And if you can build a network of LTE module address tier 1 with the Thione or SATA-BOS, then you have a sub node, which is kind of a house. One gateway connects to the satellite as well as to the cloud, and then the rest only talks locally still within 2.4 gigahertz. We are running a time a little bit short, but I think we are pretty much okay. Please ask questions that you have now. Now that takes us to GNSS applications, and I told you before, you can make a notes where can you use GNSS or a GPS. So here is some of the list. It's not only them, but you can also use them list here and some more list. These are the customers currently asking us, can we have component for, we have a product here. So for example, my favorite one is a rental bike and the gardening robots or the river boats, because these are the customers that I normally regularly deal with them. Then I must say thank you so much for your time. Thank you for attending these seminars. I hope you have learned something and you take home all these things. Come on, click. Yeah, perfect. Thank you. Thank you so much for your time, and I take any more questions you have. Okay, so one question that I have is, can we operate LTE and GPS simultaneously? The answer is, because there is a single channel communications, answer is no. If you want to operate LTE, then you switch off the GPS, focus on LTE, send your data, receive data, do something, then switch over to GPS. And trust me, if you make a product using LTE, for example, a container tracking or a bike tracker, you're not going to do all the time updates. You every 10 minutes you take the data and then upload to the thingy bob. But that's it. Any more questions, guys? No. Thank you so much for listening, and look forward to see you soon once again.